Thank you, and welcome. So glad to see so many people here. The Dave and Margie Williams Distinguished Lecture Series at the College of Engineering. My name is Chris Yates. I am the Chief Advancement Officer in the College of Engineering. It is my honor and privilege to get us underway today. This is the inaugural lecture in the series, and I want to give you just a little, no pressure. I want to give you just a little bit of background. Former Dean Williams, Dave, could you stand for a second? I appreciate it. And Margie Williams, his wife. When Dave was Dean of the College of Engineering, he had a vision for a lecture series that would bring to campus lecturers who were outside of the normal academic realm, and to bring perspectives from industry, from government, from philanthropy, a whole range of other perspectives to expose our students and help them gain that other perspective. So Dave got that series underway, and then not too long before his term expired, as Dean, he and Margie generously decided they wanted to endow this lecture series so it will go on as an endowment forever and ever, in perpetuity. So I want to say a big thank you to Dave and Margie for all you've done. Thank you. I'd like to now turn the podium over to Professor Anish Arora, who is the chair of our electrical and computer science and engineering.
Computer science and engineering.
Oh boy, I will make that mistake.
This is computer science for you.
Yes. You will take it over.
Yes. Thank you, Chris. Nothing makes our department and our college more proud than to see our best and brightest come back to visit us. And this is sort of the picture perfect example of that. Steve came here for his bachelor's. He did his master's, he did his PhD. He was a member of our research faculty, and he did all of this while knowing he was interested in computer animation. So it's absolutely no surprise that he chose the right place, and that he went to the right place. That place called Pixar Animation Studios, that mecca of computing and art. And he has contributed over the last 24 years in many, many ways, which have made him the Chief Technology Officer of Pixar. Now, what does that mean? It means basically he does everything. So certainly, he looks at what software R&D is needed, what information systems are needed. They've had some fantastic software that Pixar is known for, something called RenderMan. And I think Steve may have understood RenderMan better than most anyone, I'm told. And then he's looked at all the visual effects processes and systems that that company needs. So, pretty storied journey. His first movie was, what, Toy Story 2? Your first credit, yeah, as a technical director. I think you did something on simulation and modeling there. And then the next movie was Monsters, Inc., where he pioneered a new kind of technology. So there's this character called Sullivan, and that look of that is thanks to this gentleman here. And so then he goes on to do a number of other movies as a supervising technical director. So movies like Finding Nemo, Cars, Up, Brave. And by the way, everything I've named so far probably has some kind of an award to it. So an Academy Award for most of them, for these movies, and a Golden Globe for other movies. So, Steve, welcome home. We are so looking forward to hearing the story of your experience and your insight and your initiative. So some of us will no doubt be very affected by that. And I just do one piece of logistics before I give the floor to you. So you'll see that there are little cards with a pen somewhere on the table in front of you. Please feel free to jot down questions. And as you jot down questions, if you'd like to share them, just wave them. And I or one of my colleagues, Sheila and Katie, will come by and get them. And then, after Steve finishes speaking, we'll have an interaction session where your questions will get posed. I get the honor of reading them only so that everybody can hear them clearly. But please feel free to continue that conversation as we go along. So without further ado, I give you Steve. Thank you.
Thank you. Very good. I saw the cards and I thought they were for keeping score. So I'm leaving it just for questions, although my wife's like, Rich, you got the card. My wife Gwen is here with me and our friends Beth and I from California. And we both have sons that are really good friends. Our son decided to stay in California. Theirs chose Ohio State, so he's a student here. All right. And now, so clearly they have the smarter kid, smarter kid of the two. And now they're getting the full exposure of Ohio State on the game is unique. Californians don't understand the level that football plays. They just don't have any idea. When I'm watching here, I'm like, oh, of course, Scarlet and Gray, chairs and tables. you know where you are. You don't have to think about it. This is just a test clip I brought from Lightyear. Hi, my name is Steve May. I am Chief Technology Officer at Pixar Animation Studios. I, as mentioned, got my degrees here, including my PhD in computer science. I studied computer graphics back in the 1900s, as my kids would say. I stole this title, The Illusion of Life. There's a famous textbook about animation. If you study animation, you might know about this textbook. I've been at Pixar for a while, and you sometimes kind of forget how cool it is. That we make things that feel like they're not real, but like they're alive. The characters in our movies, it's really special. It's really still magical to me. And what's also interesting is that there's a ton of engineering and technology behind every frame of animation that we make at Pixar. So that's my one takeaway from this room is that you all know that is true. That behind every frame of animation, a lot of technology, a lot of engineering, and I think that what drew me to Ohio State, what drew me to Pixar is combining things that maybe seem kind of different in some ways. So for me, it was art and science were the things that excited me about this. I'll talk a little bit about kind of how I got to Pixar from Ohio State. I'll talk about the interplay of art and technology and how that impacts the way we make our films. And I'll show you some of the kind of latest and greatest technology that we're working on at the studio right now. So like I said, I always loved art and technology. I was always drawing when I was a kid, building models. My dad liked tech gadgets. He was always bringing home the latest, whatever. He was the guy who brought home the beta VCR instead of the VHS. For those who remember videotapes. And he brought home a personal computer. It's like one of the first people I knew. We were one of the people I knew that had a computer, and that really started my love of programming. And as a kid and as a young adult, I always looked for ways to combine these things. In the 1980s, software was not that easy to come by. There was no app store, you couldn't just download a fun game. It wasn't even easy to buy games, really. But one of the things you could do is you could buy magazines, and they would print code in the magazines for a game, and you would type in the game, and then you play for like 5 minutes, because they usually weren't that exciting and good, and then you would go on to the next article and type in another game. And that's basically how I learned how to program. My high school didn't have any computer science or programming classes, so that's how I learned. When I was 15, I wrote this game, which is called Diver. It's like undersea action adventure game. And it was published in this magazine called Antic, which was for Atari computer enthusiasts. So Atari, the famous video game company, actually once made computers. And I wrote the code, I did all the graphics. They even cut and paste my graphics, my beautiful articles, and my logo into and all this stuff right into the magazine article. And that was kind of my concept of computer graphics, was this kind of chunky 8-bit graphics that you saw back then in computer games. Until I saw this magazine, Science magazine. And I couldn't believe that this image wasn't real. The pool balls really looked real. The hand actually is a photograph, but the pool balls were computer generated. And this magazine, it talks about 2 places in particular in the article. And the first one was Ohio State. And the second place was a computer division of Lucasfilm, which would later become Pixar. And I basically read that article as a kid, and I'm like, that's it. That's what I'm going to do. This is amazing. I'm going to go to Ohio State. I'm going to go work for this Lucasfilm place. Tom Porter is the computer scientist who made this image. He's very notable in computer graphics. He invented things like compositing, which is a pretty fundamental piece. And the funny thing is, he ended up being my first boss at Pixar, and he's actually in the office immediately next door to me today, after all those years. I love my time at Ohio State. I took every class and did every project I could related to computer graphics, just everything possible. I worked at ACAD, and I did medical visualization with Don Strenny at the Ohio Supercomputer Center. I worked on a couple of our own animated films. I wrote the animation system we used. I wrote the renderer that we used. I also studied under Wayne Carlson. He was my closest mentor and advisor. Wayne was a professor of computer science. He was director of ACAD. After I left, he was chair of design and also a vice provost here before he retired. Wayne is an amazing person. While I was at ACAD, I taught a class called Digital Lighting. I'm pretty sure I wrote the very first website, this was the early 90s, for teaching how to write shaders using RenderMan. And shaders are basically short programs that generate patterns and surface materials, looks of objects, 3D objects. And what was fun about that class was that it was at ACAD, so it was a course for art students who did not have backgrounds in programming or math, and they really would come into that class and say, well, I can't do this, I can't write code. Sometimes I've even been told, because I'm an artist, I can't do stuff like that. And I was like, hold on, I got you, we'll do this. And by the end of the class, they were writing programs, including like this image on the right. And it was really meaningful to me, inspiring, that, and it's kind of influenced how I think about things today, like bring art and technology together and really support people to try to do things that they didn't maybe think they could do before. I also had the great fortune to work with Charles Surrey. I could do a whole talk on Chuck's life and career. He was a remarkable artist. He's also MVP of the first national championship football team at Ohio State. He's often credited with being the father of computer art. And I wrote the animation system that he used for his later work, including the image up here, horseplay, and a lot of this, and the image that's behind us in the photo. And we spent like hours, we were out there on the weekends together, no one else was there in the lab. And we would talk about the interplay of art, fine art, and technology. And he was an advisor in my dissertation. He was a really close friend of mine. We still email up until his passing earlier this year when he, at the age of 99. After Ohio State, I went to Pixar. I have been there for 24 years. The latter half as CTO, as Chief Technology Officer. I sometimes apologize about that title, like, I'm CTO, but I used to work on the movies. I used to be a creative supervisor. Worked on a number of films that are now so old, they're called classics. As mentioned, my first credit was on Toy Story 2, which was released in 1999, which is 23 years ago. But I worked on a number of other films. I was a supervisor on almost all of these, and usually worked about 2 to 3 years on each one. So yes, they do take a really long time to make. This is something we say a lot at Pixar. Art challenges technology, and technology inspires the art. You're probably sensing a theme here in my talk. This phrase is not only something that we say regularly at Pixar, but it has a lot of meaning to me. Steve Jobs, you may not know, after he left Apple the first time, he actually came on and he bought Pixar from George Lucas. And that's when it became Pixar. He was CEO for 20 years. And he also believed really strongly in this combination of art and technology. He believed in it so much. This is a picture of the outside of our main animation building at Pixar. And it's named after him now because he designed it. And it was basically built to support this kind of interaction. So this is the atrium. So you walk into Pixar, and I'm giving you a tour. I would say, like, here's the atrium of Pixar. This thing was built to design the interaction of artists, technologists, and other people who work at the studio. It's right in the middle of the building. The coffee shop's in there, the cafe, the restrooms, the conference rooms, all lined at the second floor of this room. So basically all the kind of day-to-day functions that might get you out of your office are all in the middle. So people just naturally run into each other when you're doing those things. And I always say, every time I get a cup of coffee, I learn something that I didn't know before I went in. So, as mentioned, I worked on Monsters, Inc. I talked about this a little bit. And it's a good way to explain how art and technology come together at Pixar. My very first, so my first credit was working on Toy Story 2, but actually my first job was working on Monsters, Inc. During Monsters, Inc. I did a little job on Toy Story 2. But when I started, it was all about this. And the process is very iterative. Art is an iterative process, whether it's the design of a character like Sullivan, or developing a story, or building some new technology. We don't know the answer when we start. We have to find it. Making movies is messy, creative endeavors are messy, and technology is a creative endeavor. This is one of the early designs of Sullivan from Monsters, Inc. You see it's pretty different if you saw the movie. This is not what Sullivan looks like. This is kind of where we start. Here's a version where Sullivan had tentacles and lots of eyeballs. It actually made it into Waternoose, one of the other characters in the film. This was kind of an evil-looking version of Sullivan. I see why we moved away from that one. There are these kind of scary versions. This shows you how wide a range of things we try before we land on where we want to be. This is getting a lot closer to what Sullivan looked like in the film. Here's Boo. And so when we start out making a CG character, we take drawings like this. Often they're just pencil drawings. Sometimes they're literally on napkins or back of stationery. At Pixar, we take storyboards, 3D sculptures made out of clay, detailed drawings. These drawings specify the colors and patterns and the exact shape and direction of the hair and fur. And while all this was happening, the character design was in flux, the one thing was really, really clear to Pete, who was the director. He said, I have to have this main character have fur. And that's fine, except this is the early days of computer graphics. We had never animated fur. In fact, fur really hadn't been animated in any CG film or even live action films, except in very, very, very small amounts. We were really good at toys and bugs. Things were kind of plastic, had smooth surfaces. But we had never had a character with fur, and Sullivan would have millions of individual hairs, right? Each one had to be modeled, shaded, animated, lit, and rendered, and we didn't have software for any of them. The most mature part of our pipeline was that renderer, RenderMan, that we're kind of well known for, but it could only render a few thousand hairs, not millions. And it didn't even have a way to do shadowing on hair. So the hairs couldn't self-shadow each other, and hair does not, one of the things I learned right away, hair does not like hair without proper shadowing. So to solve a challenge like fur on Monsters, Inc., we do this kind of iterative cycle, and this cycle can take years. I worked on Sullivan for 3 years, including working on a lot of the shots in the film. And we start with research. We do pencil tests, like the one on the left. We studied animals on fur. We had actual samples. I had a poster board with mama fur like shaved off and stapled to it, kind of gross. I had this little funny thing with one of our art directors. We would like send it back and forth to each other's office just so we didn't have it in our office. Went to the library. It was the research on the physiology of hair. And then we just started doing tests. So again, it's an iterative cycle. It's a messy thing. At that time, when we first started, this was what Sullivan looked like. He wasn't called Sullivan, he was called Johnson. And we were pretty serious about this version. This is the very first animation test ever done at Pixar with dynamic fur. It uses that early design, it's got tentacles. We also decided we didn't want to do tentacles after we did this test because they were really hard to animate. It was all prototype software. We ended up replacing all of it that we did for this test. And you can notice that it was done in 1998 and the movie came out in 2001. So it did take time. We show tests like that one in a meeting called Dailies, where artists show their work. You get, on a daily basis, you get feedback. Your peers are in there, your bosses are in there, the director's in there, giving you notes, and you go back to your office and you refine and work on it some more. But it's cool because it creates this environment where you're getting daily feedback and critique every day. You get very used to people giving you constructive notes about how your things can be better. So this is the next animation test we did. Sullivan has brown fur, so I think we thought like, well, maybe it's because it's blue that it looks funny. Maybe you make it brown, because there are no creatures that I know have blue fur. You make it brown and easier, it still looks weird. It's not really working very well. It's kind of funny because Mike Wazowski, he doesn't have arms. At this point, we're kind of playing the idea like him not having any arms. We changed our mind on that too. But the fur is kind of like passing through each other. It's kind of silky and clean. So back to my drawing board, or in this case, it's my notebook. So I had this notebook where I used to all my notes about fur and everything about it, notes, pictures, code, math, and just kind of like thoughts like, what makes fur look like fur? It was not something that we knew how to do. And it was not something that was written or published about. And so like looking at this photo, like the key characteristic was like, oh, fur, like it clumps together. You know, the oils and dirt and fur like kind of make it kind of adhere to each other in certain areas. So that's what gives you like this humping, furry kind of feel. So let's make nearby hairs on Sullivan's body have similar shape. Well, that was a simple idea, but making something look good is hard. And I have to think that at this point, my bosses are probably like, I don't know if this is going to work out. Because this looks pretty awful. Like it comes like cobwebs on the one on the left, and it's like kind of a weird sweater on the one on the right. So this is like big, just fail. So move on. There's that thing that anyone who studies math knows about called Voronoi diagrams. And so the aha moment was like, oh, what if I use a Voronoi diagram, put that on the surface of the skin, and grow the hairs out of those different cells, and all the hairs that grow out of a single cell will have a similar behavior or characteristic. Maybe that'll make things look like fur. So went back to a very simple model, got away from the complicated character model, and made a hairball. And this was the very first test. So I submitted this at night, again, came in the next morning to see the results, so you didn't wait that long to see the answer. I was like, finally, we've got something that kind of looks like fur. Started having some fun, like doing something kind of wet, or something kind of like a Spanish water dog. Just for fun, to see what other kind of looks we can get out of this. So we don't know where this is going to go. This was the next version of Sullivan. So this was Sullivan number 2. This one was called Mulligan. Because we planned to do it over. So this is going to be a do-over. But this was our first successful fur test. This was this actually is going to work. He's got that scowl, by the way, just because we had no animation controls for his face. So that was about a year of work to get there. Steve Jobs was, I mentioned him earlier, he was particularly focused on this thing of fur. He's like, this is the thing, this movie. So we were a little nervous when we showed him that test, and he loved it. We went outside and had some beers together. I don't think he gave it to us. Steve didn't like drink, but we were very relieved that he liked the test. But it didn't end there. So we're kind of used to make story changes. We will do whatever it takes. If we need to make the story better, we will find a way to change the animation. At the end of Monsters, Inc., we kind of heard this rumor like, hey, Story is working on this idea of Mike and Sully going to the Himalayas. No, this is really the last few months of the film. You gotta be kidding. It was true. My friend and I, Michael Fong, he was that person that we really worked closely on the fur. We went to the art department, we found this pastel. We're like, it's true. He's going to the Himalayas. And the good part was that early on, Pete, the director, kind of liked this idea of Sullivan having dirt and debris in his fur, like a real llama would have. And as we made Sullivan, we made him nice and clean first, and we kind of got attached to that version, so we went with that. So we didn't ever use that dirt and debris thing, but when this came up, I'm like, oh, maybe I can use what we built there to actually put snowflakes in his fur, and that's what we did. So that came in very handy. So I wrote the software to make the snowflakes. They moved with each hair. They accumulated over time. So as the shot goes on, the snow gets further. I think this is where my Ohio background came in handy. Things like have the wind direction, where he landed on the ground. And after writing this code, I animated all the snow and special effects in the shot. To this day, this shot is probably what I'm best known for at Pixar. So Pixar has a really, really long legacy of research in computer graphics, computer science. I mentioned a couple things already, but we invented things like compositing, subdivision services, particle systems, character animation, many areas of rendering, including motion blur, shaders, the raise algorithm, and RenderMan. But we'll talk about what's happening now. What's the latest and greatest at Pixar? So let me show you some things we're working on today. The first is Presto. So Presto is our proprietary animation system. I think it's the best animation system in the world. We don't know who use it, so no one else gets to know anyway, so I can say that. We use it for layout, which is the camera and staging process, for hair and cloth simulation, and look development. And this is one of our directors of photography here doing some camera layout. But I'm going to focus mainly on what we're doing for character animation. That's probably our main emphasis in Presto. I mean, we built Presto with our animators to provide the most sophisticated tools possible for them. We have these pretty unique, a variety of different kind of interfaces for them. This is Miguel from Coco. He has these high-level controls. You can just grab them, and notice when you move his chin, his nose moves too. So you can have very, very fine tooth control, and also kind of some high-level controls. We have really advanced tools now for dealing with hair, including real-time hair rendering. So before I had to wait overnight, now you can see it in real time. We've come a long way. This is Helen from Incredibles. She's got hundreds of thousands of individual hairs. Our Presto can draw them all, and allows them to be interactively modified. Yeah, really wish we had that back on Monsters Inc. One of our most recent films is called Luca. I really loved this movie. The main characters are sea monsters. They transform from human form into sea monster form in and out of the water. And we really fine-tune the exact timing of when those transformations happen and where they happen. So we built in special features into Presto so that we could see that monster effect live. And we can specify exactly where it happens and the exact timing of it. So it's that kind of the shading, the geometry, everything that goes along with this kind of really cool transformation effect. So it's pretty cool stuff. One of the hardest parts of what we do is character rigging. So this is, it's getting these very precise shapes. Character silhouettes in animation are one of the most important things that we try to strive for with animators. The silhouette really has to read the action. So really clear lines of action is what we're always trying to achieve. So the exact shape is extremely important. We build in these animation controls that pose the character. So here's an elbow bend control. So it moves the arm, and then there's a whole bunch of mathematical deformers that shape the rest of the arm to try to hit the desired shape. The desired shape is where you're seeing those white curves. So you can see in some poses it looks okay, like where it starts out, but then as it bends, it starts to get really weird and uneven looking. So we built a new thing just recently called profile movers, where we actually specify those white profile curves, those edge curves, and it applies an additional deformation that helps match the exact shape. As you can imagine, this is a lot more direct and intuitive than trying to build a bunch of deformations to move all those individual vertices and all these meshes. The first time we really used this was on Turning Red, which was a film that we released earlier this year. It's a great film. If you haven't seen it. Has an interesting challenge. The main character is named May. She's a teenage girl. Is highly expressive, and she gets turned into a red panda. She turns into a red panda when she gets stressed out. So I'm sure it's bad for that. So here you can see a little walk cycle. We do lots of tests of our characters. You can see the profile curves are on the left, and they're like a network. So we actually call this a curve net. Not very creative, it's a network of curves that define the shape. There's another one where you can see her running. You can see the profile curves. But you can see that there's actually a relatively small number of these profile curves versus the thousands of individual vertices that are under the hood. This is part of why it's easier to use. I'll run to that same thing. This is I just kind of grabbed this because it's cute. It's a bunch of poses. This teenage girl, red panda. Keep going. And as a spoiler, if you haven't seen the movie, there are more pandas. But one of the great things about this technology is that actually it's portable, so we can apply it to different topologies, different mesh topologies, without changing the deformations themselves. So we can really quickly make a bunch of more characters like these. RenderMan. So RenderMan is our kind of industry standard software for doing 3D rendering. Does really high complexity, state-of-the-art imagery. It's the first software ever to win an Academy Award. Presto, by the way, is our most recent software to win an Academy Award, which part of my sales pitch is if you work at Pixar, you might win an Academy Award. If you write software for us, or if you make movies. So RenderMan takes a massive database. This is from Toy Story 4. It takes materials, the geometry, the lighting, the camera specifications, and it produces the final rendered frames. These are all frames from RenderMan, which shows kind of different layers phasing in here. Rendering is really computationally complex. So this is kind of a simple shot in the world of cinematography. It's like an over-the-shoulder shot of two characters. This takes 350 hours of CPU time to render one frame. And we did it did take longer. We did optimization to make it that fast. But the upside is that the renderer does a lot of really complex effects for us. Like in the background there's like chandeliers and lights, and you're getting these cool refractive effects. And you're getting the bokeh from the camera, you're getting depth of field. I mean, all these things are coming, and they really are things that we used to kind of handcraft or cheat, and now the renderer can just compute them automatically, but it's expensive. The antique store. So the Toy Story 4 is an antique store. It's actually one of the most complex sets we've ever built. So you wouldn't probably think, oh yeah, the antique store, that's going to be one of our pinnacles. But it has thousands of detailed individual props. This is a RenderMan test render. It starts with the empty antique store and it's filling in the props from back to front. You can just see how many things are in there. So this is not a photo of the antique store. This is like a render from RenderMan, and it's just bringing in all the props. And you can see how much stuff is in this antique store. It just keeps going. But wait, there's more. So we also model dust and debris. This is a lineup of models we built of individual pieces of things that we drop and set dress into the scene. And then we also build spider webs. So these little red dots you can kind of see moving here, those are individual like little AI spiders. And they build webs. And then they build webs off of those webs. And they just keep going until you tell them to stop. But we use that also to add spider webs into the antique store set. This is what a frame looks like from the film. So we want real time. We don't want 350 hours per frame. So I want to talk about that a little bit. The definition of what real time is varies. It just depends on like what thing you're doing. In film, we measure film in 24 frames per second. Video games, we like 60 frames or higher. And VR might be 90 or 120 or even higher frame rates. But I'll just talk about film. That means you have about, if you want to be in real time, that means you have about 0.04 seconds to render a frame. If you want to be real time. Our normal film renders take about 60 hours on CPU. We run those on multiple cores, so that cuts it down to more like 8 hours. And then just so you know, like we have a big farm, render farm, big data center. We ship out all the frames in parallel, so they all go out at the same time. But still, 8 hours. And that means that our actual time per frame we have right now is 28,000 seconds. There's a lot of zeros difference between real time and where we currently are. So we're doing a number of things to try to bridge the gap. We're working really hard to leverage GPU technology. So the GPUs have gotten extremely powerful at this point. It's allowing us to do renders now about 100 times faster than before. We built a brand new architecture called RenderMan XPU. This leverages GPU and CPU or whatever you have available to you to be much faster. You can see this render here is almost interactive. Right? It's a fairly complicated set. It's not the antique store. This is a side-by-side from Luca that will show our CPU renderer on the left, the old renderer, our current one, and the new one, XP, the GPU renderer on the right. And I'll hit the go button. Don't blink. You can see how much faster the new one is. So the XP's already got a render that fast, and the CPU one is on the left, and it's starting to build in buckets here as it draws. And then the XP is actually still running. It's refining. You see it's a little bit noisy, and over time it'll get less noisy. And I'll talk about that more right now. So we're also doing a lot of work in AI and machine learning, and there's some really amazing things that we're able to do now. So the rendering technique I just showed you is called path tracing. It simulates the physics of photons, individual light photons, and it uses Monte Carlo integration, which means we use a lot of point samples. And if you don't do enough samples, you get noise. And I don't know if you can see here on this frame. I'll show you some more extreme examples. Like there's noise in this image. If you saw this, you know what happened to Pixar, what they do. And this shows 64, what we call 64 samples per pixel. Okay, so every pixel has 64 samples. And then we run our AID noiser on this, and it removes the noise. Again, here's the noisy version. As it wipes across here, it's going to show you how it denoises that. And all it's taking as input is just the noisy image. And from that, it can predict the clean version. Here's a more extreme example. And here, you can see like that's pretty lame. And the neural network on this is going to predict a final image based on just those pixels that are there. And it even adds like detail in the hairs and things like that. Yeah, it's pretty interesting. We trained this mainly on, so we did this as a joint project with Disney Animation. We trained this on Moana and Cars 3. And it works really well in humans. In fact, it's used on all the Star Wars content from Lucasfilm as well, without using Cars training data and Moana training data. Here's Socks. Socks is a very popular character from Lightyear. So this is one sample per pixel. Like, you think barely enough information at all, and this is what the denoiser creates. It's not perfect, and we would not use this, but it's still kind of remarkable, like just how you know, the inference that it can calculate based on a small amount of data. So we're also doing denoising now on GPU, so it can be very, very fast. That with some new algorithms, increasingly fast GPU hardware, like we're getting there. Like we are going to bridge that gap of that real-time memory problem. So we're always looking for new ways to apply technology to make better movies. And one area we've invested in a lot lately is to improve the diversity of the characters in our films. So, for example, we've had some software for a little while that can look at the movie scripts and the character names, and it can give us a breakdown of lines based on gender. And that's been super helpful. But there was more stuff we wanted to do for Soul. You know, analyzing the script only tells you about lines of dialogue, right? It doesn't tell you actually who's on screen. So we worked really hard to try to get the right and appropriate diversity on screen. And for Soul, a lot of Soul takes place in New York City. New York is a very diverse place. It would not be right if we did not get that right. It wouldn't look authentic. So typically what we do is we have a catalog of background characters, and then we kind of set dress these, we cast these crowds by picking characters from that catalog. And on Soul, I mean, it was very intentional. Like, you want to have the right diversity in these shots. And we set some goals. We said, let's have 80% people of color, 20% white, and like 50-50 male-female. That was the goal, right? So from the very get-go. So we started building the shots. And then we started tracking and counting by hand. We found that we were actually 50-50 people of color versus white, and 30-70 female-male. Even though like we set out to have completely different ratio, we were getting the wrong result on frame. So we built this software into our existing kind of production tracking software that helped automate the process and to tell us what we're doing right and what we're doing wrong. So we added metadata for every character that has like ethnicity, gender, age, ability, body type. And then the software produces statistics. And it shows us how we're doing at the shot level, at the sequence level, at the show level. And it's dynamic. So as we build shots continually, we can always go back and look at this and see how we're doing. We have different ways to view the results. So in this view, we can compare the actual data with the goals. And in the end, I'm happy to say, like, Soul was kind of exactly the way it wanted to be. It's 80% people of color, 20% white, 52% female, and 48% male. And having accurate tracking and this new software was key to making it one of the most diverse shows in Pixar history. And it's not rocket science. This is not that hard to replicate. We did the same thing on Turning It Red. Doni Shi is a Canadian Asian American, and she was like, the scenes don't feel quite right. I grew up there in Toronto, and this doesn't feel right. And we ran a tracking software, and we found there were issues, and so this is the after on that shot. Again, this is the before, and this was the after we had updated things. So the last major thing I want to talk about is called USD. So this is a thing Pixar created. We open sourced it in 2016, and it's becoming kind of a big deal. A number of experts and companies outside of Pixar are calling it the HTML of the metaverse. What? How did this happen, and why did Pixar do it? Well, when we created USD, we were not trying to solve the problems of whatever the metaverse is. We were just trying to solve the problems of making our movies. We were trying to make complex scenes like the antique store. USD, Universal Scene Description, is used to describe everything in the scene. So it's like a definition, a recipe of everything that's there. The geometry, the shapes, the cameras, the lights, materials, and everything. It can handle really massive scene complexity. So the antique mall is just part of a bigger set. The town, it's part of this town, the carnival. This is all represented in USD. And this video shows an interactive tool that's included with USD that allows an artist to browse the entire landscape, the town, the carnival, and then move inside the antique store where every prop down to the very smallest can be inspected. So you can see all that stuff is all right here. It's all viewable and inspectable. We even use USD to encode the lights and the light patterns in the carnival. How much like a real carnival? And we think that USD allows us to do scenes that are about 100 times more complex than we could do before. So USD allows us to make really complex virtual worlds. So there's a connection there, I think, the things that people are talking about with the metaverse. The other thing is that it's portable. So every piece of software that we used had a different file format and a way to describe 3D data. So as you brought data into one tool, it would look different, or you lose information. Or you had to do a whole bunch of work to do that importing and exporting or converting of one thing to another thing. So USD kind of solves that problem by being universal, and that it can encapsulate the data for all of these different applications. This shows some tools we use in-house, so the same scene data looks the same in different tools. USD has been adopted by game engines, so like Unity and Unreal. So we leverage that to build a VR application for location scouts. And this set dressing prototype that we built for our movie called Onward. And USD adoption goes outside the film industry, so this is something we didn't really anticipate. Apple has adopted USD as its primary format for 3D data. So if you're looking at something in 3D on your phone, it's an iPhone, it's probably using USD. And allows us to view assets from our films directly on Apple devices, and including things like AR. NVIDIA, which is the largest GPU maker, has built an entire platform on top of USD called Omniverse. And they use it to make it easier for their customers to create things, everything from like really large scale simulations, like whole Earth weather forecasting, as well as building digital twins, which is this idea of building a digital version of a factory, say a car manufacturing plant. You build a digital version first, you test it until you refine it, and you run simulations on it until it's 100% optimized, and then you build the physical plant from that digital version. That's called a digital twin. They're using USD to now build these twins. A variety of companies. I met someone earlier this week. Lowe's, the hardware store, is using USD to model out their stores and optimize things like what goes on the shelves. Pretty wild. So portability is a key thing to sharing assets across different platforms. I showed that USD can be used to create complex 3D worlds, but the way it does it is very important. So I'll go into a little bit of detail here on USD. So a scene in USD is not a single asset. It's actually a web of interconnected 3D assets in a way that's similar to the way the web pages work. And the web of assets is described in layers. So if you're familiar with programs like Photoshop, the image on the left, you're used to like dealing with separate image layers that then you can edit and then get composited together into the final image at the end. USD does the same thing, but it does it for 3D scene data. So you can have people editing different layers, and it's non-destructive. Changes in your layer will not affect someone else's changes in another layer. With USD, a shot in a film, like the way we do it, can be comprised of separate layers for each department. So each department can do their work in their own layer and do it non-destructively. And that way it doesn't impact the work that's done by other artists that might be working at the same time. This allows multiple departments to all work simultaneously. Right, so in this way, USD is fundamental for us to supporting artist collaboration on complex scenes. A lot of people can be working on the same shot at the same time. And then USD knows how to composite these layers. So it knows how to combine them. And values in stronger layers override values in weaker layers. So for example, layout does the staging and rough poses for each shot. Then animation comes in and overrides those layers with their own final poses for animation. Sets and effects at the same time can be working as animation, and they don't break each other's work. And the number of layers is arbitrary, and USD puts no limit on it. So each department can have as many layers as they want. In our animation department, it's not uncommon for every animator to have their own layers, so they can all be working on characters at the same time. So here's an example from Brave. It's comprised of multiple layers. So a character model has many layers. This is Merida and the bear, Mordu. And that's the shot layer that's shown on the left. And then on the right, in the middle here, are the models themselves. So each model, like Merida, has references to separate layers for body geometry, hair, cloth, and materials. And a character artist can modify the geometry or the shading of Merida in the model layers without breaking animation poses. And then each character model references layers for the underlying articulation rig. And each rig is made up of layers too, so it's just this on and on kind of thing. So in this example, a generic rig for a left leg is referenced by Merida once and Mordu twice. Mordu's got two left legs. And any future fixes to that left leg rig will fix both characters. So the process by which those layers are combined back is called composition. Let me show you like a more moving example. So this is Squishy from Monsters University. He's quite the dancer. So imagine we get like a very late note that we want to change the shape of Squishy's horn in this scene, but it's like, we're almost done, kind of like the Himalayas from Monsters, Inc. Animation lighting are done, Squishy's in a bunch of shots in this sequence. And if we have to go in and change Squishy, we might break all the other stuff that's been done. So the good news is that USD and layering gives you multiple options. So here we are in Presto. We have 2 shots, one on the left, one on the right. And I can play back either one. So here he is in the one shot, here's going to play back in the other shot. And if we work in the shot layer, so we're working on that single shot, we can make changes to the horn geometry. It will only override the shape of the horn in that shot. So here we're going to say we're going to edit just the shot, and we're making changes to that horn. It's only in that one shot, that West Street shot there. But instead, if we modify the geometry at the higher level, right, in the sequence layer, then it will change the horn for all the shots in the sequence. So now I'm changing it in one shot, but it's changing it at the layer of the sequence, so it's affecting the other shot too. I can also change it, we also could change it for Squishy, right? And that will change all the shots in the film. So here when we change the kind of the base model, now if there were 10 shots that would be Squishy, they would all change, or 100, they would all change. And we can even go and change the horn. So maybe the horn is used as a layer in different monsters that have the horn. So now if you change the horn, it'll change all the monsters that use that horn in the film. So if you're trying to build 3D worlds for the metaverse, you want to build really complex worlds. You probably have a lot of simultaneous users that are editing, interacting at the same time. And you need to be portable so that it can be moved from platform to platform or from device to device. You want to be able to take your digital 3D assets with you. So that is kind of a nutshell why Pixar's USD is being called the HTML for the metaverse. Pretty exciting and pretty scary at the same time. So that's a few of the things we're working on at Pixar. I could probably do a course on this. There's so much stuff that we're doing, but I want to talk about computer graphics. Computer graphics is happening. It's really exciting. There was a heyday of computer graphics in the early 90s with Jurassic Park and Toy Story. It's kind of like, oh, these things can be used to make movies, which is cool. It's happening again. And I'm really passionate about computer graphics, and so I'm excited that we're at this place right now. And so I just want to mention a couple of things of where computer graphics is really, really happening. So animation and visual effects, give you the rundown there. It's still a very important part of everything that you see on screen or on streaming. In fact, there's more content being made than ever because there's so much content being produced for all the services. So there's more work than ever for the artists and technologists that are producing that. Machine learning, I mentioned that thing that we do with machine learning to denoise images, but machine learning requires a lot of computer graphics. So when you're doing autonomous driving, you don't actually drive little cars around streets. You might occasionally see that, but that's just for tests. Right? What you really do is you build a virtual version of a city or town, and you drive virtual cars in those virtual 3D worlds. So a lot of computer graphics is done in order to do training for machine learning, all kinds of machine learning. VR and AR, so there are early versions of consumer devices for these. We're going to see this progress pretty rapidly over the next few years, where more and more we're going to see virtual reality and augmented reality devices. And so that's a big pull for more computer graphics. Video games is alive and well, and actually a much bigger industry than film. So video games and the level of quality and fidelity in video games is growing all the time. I mentioned they're doing so much compute power now. We can do things like this whole Earth weather forecasting. Things that's just mind blowing. So there's a lot of scientific visualization that's also happening in computer graphics. Speaking of AI, some of the AI image generation stuff from software called DALL-E, which is, I don't know if they got our permission to use that, or WALL-E, but DALL-E and Midjourney are generating really compelling images just based on strings of text. And so art and design, I think it's going to see some very interesting new tools become available. And then there's this thing, the metaverse, which if you ask 10 people what it is, they'll get 10 different answers. But one thing is that I think 3D is going to become much more ubiquitous. Right now, you might use your phone to place an object in your living room to see if that piece of furniture looks good. I think that's going to become much more common, and the range of applications for that kind of thing are going to go much bigger, especially once there's actually decent looking glasses you can wear, that kind of thing. So there's a ton of things happening in computer graphics. And lastly, if you're a student here, we do internships. Our technology ones are posted and up for a little bit, and then the production ones will be posted later this year. And if you want to know what's going on, you can follow Pixar Recruiting on Twitter. That's really good. And that's it. Thanks for
So we changed rocket science. My, is it cool? It was really powerful. Please remember to share your questions with Katie and Shayla. We have time for a few questions, and here's one which talks about motivation for doing what you do. And as you can see, we've attracted a number of young people to be motivated in this stuff. Do you ever get to meet the celebrities who do the voices?
Sometimes, yeah.
Cool.
Yeah.
Okay, that's one reason for doing.
They're Pixar's a pretty low-key place. This is pre-pandemic. Hopefully we'll get back to this point soon, but you'll see them walking down the halls, they're having lunch.
Right.
Keanu Reeves did the voice of Duke Kaboom. It was awesome in Toy Story 4, and he was having lunch in the cafe, our cafe, and they were kind of talking about the film. He got so excited about it, he jumped on top of the table and started doing like Duke Kaboom live. So you never know what you see. We also have 2 recording studios, and so they'll record on the voice what happens in the studio.
Well, here's a really forward-looking question. So do you think that these amazing new technologies that you shared today, if you project them into the future, will they result in a homegrown animation industry where individuals like, all of us here can create their own high-quality version of Toy Story 2?
Yeah, I think so. Yeah, I think what we're seeing is and we see this in a lot of cases with technology. There's a democratization that happens. 20 years ago, Pixar was the only place where you could make really 3D animation. This requires so much technology, so much specialization, so much compute. But increasingly now, there's great software that's free. There's cloud compute that you can use to deal with the compute issue, and the software will get easier and easier to use. I mentioned those image generation tools. If you're not familiar with Midjourney or DALL-E 2, you should just do a little Google search and see what's being generated by strings of text. So I think we're going to definitely see the ability for a much broader range of even individuals to make really sophisticated content. Now, making a really good story is really hard. Maybe AI will do that too. But it's interesting to see where it goes.
Thanks. And this one I thought was a rather deep question. So the question goes like this: what value systems should we cultivate that would prepare us to be a leader? I guess they're talking about you and your experience. What value systems would you encourage folks to keep in mind?
Well, that's a good question. I just go back to what I was saying earlier about my personal interest. To me, there's a couple of things. One is you really want to be true to the things that you believe in. So, like I said, I really believe in the combination of art and technology, and trying to support people to do that. I just think that's really important. I think that I often say one of the most important characteristics is to be humble, because that means you're super nice or something, but it means you're open to learning new things. That's what I find to be super important. If you stop kind of listening to others. One of the things I love about Pixar is, we just had our most recent intern class this summer. They're very young, like a lot of people here, and we learned so much from them. It's very different from the way that people my age even think about things. So I just think that's something.
Oh, that's very insightful. I totally hear you. So here's a very pragmatic question that I sort of had this in mind too. We have all these students who are in arts and sciences and computer science who are interested in this area. So what steps would you recommend taking towards the end of sort of getting into the computer animation industry? How could we prepare yourself? You clearly have a lot of interest from the best students all over the world. So what could a student at Ohio State do to prepare themselves for being competitive?
Yeah, there's so many resources, and it depends on what you want to do. So you might just want to be a story artist, or a character artist, or an animator, or you might be more interested in technology. There's so much material available. I mean, I was always kind of self-taught, probably because it weren't a lot of classes to take. But I think there's just a wealth of software. Like I mentioned, there's free software now you can download if you want to do computer animation. You can just start doing. There's no real barrier to learning. It's just in general animation, as I think I probably showed, is like super interdisciplinary.
Mm-hmm.
So like study films and draw and do some programming. But you can do all of those things. I mean, I think there's a wealth of things that you can try and experiment with and find what you're kind of really interested in. But it's super helpful if you're more interested in technology, if you still understand aspects of the artistic part of it, or the story part of it, or the filmmaking part of it. You'll find our engineers at Pixar talk very, very, very smartly about cameras and lenses, because they appreciate what is done there, and knowing more about that helps them to be a better engineer.
One of the questions was a follow-up to that. Are there, just pragmatically, are there some particular roles which are greatly in demand right now in the industry?
They're all in.
They're all in demand.
But I mentioned the computer graphics just because computer graphics is in demand.
Right.
We're lucky at Pixar. We have pretty low attrition, but it's tricky right now. There's just so much demand for people from Pixar who understand technology, understand graphics, understand making content, and because now they're being employed not just by other film studios, they're being employed by Meta and Google and Apple and technology companies because they're all thinking about those things and doing those things.
Right. Well, there have to be some technical questions, so I have to squeeze these two in. So someone was curious about, what does Pixar think about blending 2D and 3D animation together, similar to the Spider-Verse movie? Oh. Is that going to be a thing going forward?
Yeah. Well, we've done it. We've done some in the past. We did a short called Day and Night that was pretty revolutionary. That was a long time ago, at least 20 years back. And we're doing stuff today that mixes both forms. They're both very, very useful and they're awesome to use in combination. One of the interesting things about we're seeing is that for decades, we've been trying to get to the point where we can make things look real. Now we can make things look real. In fact, we can make things look real almost easier than not making them look real. The renderer, like I talked about, like they produce all these realistic effects just automatically. Yeah, so now what's interesting, it's almost like, I feel like in painting, there's a realism period, and then photography kind of came along, and it was like, well, now you can take a picture, if you want to be realistic, you take a picture. And that gave rise, I feel, to like expressionism or abstract art. That's kind of maybe where we're going with computer graphics. It's like, okay, we can make this look real. Now, how do we make them really unusual, more stylized? So, even though Pixar's always done stylized things, our characters are always stylized. I was talking about Bob from Incredibles. He's like ridiculous proportions. No human has ankles that big and a chest like this wide. Or Carl from Up. Carl was like this tall, but then his head was like this high and square. But we're doing more experiments with more kinds of stylized, kind of 2D-ish kinds of looks, and just experiment. It's fun time.
Great. So let me see how we're doing on time. We should probably get to the last couple of questions. There's a lot of questions which are still pouring in. So here's someone who says, they read a New York Times article about Jason Allen winning the Colorado State Art Fair through AI-generated art, which stirred quite a bit of controversy. So do you have any opinions about that, on AI to generate hyperrealism?
I'm not familiar with the article. It is interesting. I mean, again, this is the Dolly and Midjourney and there's a number of, there's like a flood of these tools now. Right. Where you say something like, show me a flying, horse over New York skyline in the style of a painter. And it produces an image in seconds. It's like, it looks like someone spent a lot of time crafting it by hand. So, now it's like, oh, if I can type text in clever ways, I can make art. What's that mean? And so, I don't know. Like, we're not sure. On one hand, you say like, oh, this is going to replace my job as an artist. I don't think so. I think we look at it as another tool. Another way to be expressive, another way to be another artist tool for artists. You can't, right now, there's not a lot of control you have over these images, other than having a different text that we're looking at. And that's a big thing for artists, is to have very specific goals in mind. But it's really interesting. I saw there was a graphic novel that was published. The author is not an artist, so he wrote the graphic novel and then generated all the images in it using Miniature. And so you're like, well, that's kind of cool. Like, here's a person who didn't, can't draw, but they were able to now make a graphic novel because of this technology. That was pretty cool. Very.
That's really cool. Yeah. So certainly AI will only add to the power, not take away from the power that you're constructing.
Well, I mean, it's like a lot of technologies. Like and I think for this group in particular, and people in universities, it's like you can use these things for good or evil, and we're all here to make sure they can use it for good.
Yeah. And of course, by the way, someone did want to know, are you making a movie right now?
Oh.
Can you tell us?
Well, I mentioned like our movies take like 5-6 years to make. 5 or 6 years to make, and so we have, we'll have like a dozen movies at a time that are in some stage of development or production. So our next movie is called Elemental, and it will release next June. And it's super interesting, and it's not photoreal, it's stylized, but it has characters that are made out of elements. And it's kind of a metaphor for different ethnicities.
Neat. So cool. Well, my dean, Dean Diana Howard, couldn't be here today, but she was very delighted you could come here. So this is a gift from her to Steve May. And Steve, thank you so much for coming here and sharing all this with us. Thanks.